Hello everyone, I'm Thibaut Issenhuth, a PhD student from Criteo AI Lab and École des Ponts. I will present a work that has been done in collaboration with Ugo Tanielian and Jeremie Mary from Criteo and David Picard from École des Ponts. This work is latent reweighting and almost free improvement for GANs, and it is about improving the sampling quality of a GAN, and especially improving the sampling quality of a pre-trained generator. So the first question is, why should we care about this? Isn't it enough to take a pre-trained generator, state-of-the-art generator, and sample from it? The question is no, because GANs have a common flow. Their output distribution is connected, and thus it cannot model disconnected distribution. So on the left, an example of WGAN GP trained on a mixture of 2D Gaussians. You can see that WGAN GP generate points lying in between the modes of the real data. Those points are very low quality, low precision points. On the right, you can see samples from StyleGAN2 trained on Olsen Church, complex datasets of in the wild church images. And here again, we can see that the generator will produce some low quality, blurry, noisy images. So in our work, we propose a method, a model to remove those low quality points from a pre-trained generator. So what we propose to do is to directly modify the latent space distribution with latent importance weights. So the latent distribution gamma will be replaced by a new distribution, gamma phi, which is the product of latent importance weights W and the original latent space distribution gamma. And doing this, we can simply model the latent importance weights by a small feed-forward neural network that takes as inputs latent vectors and which outputs real numbers, real values. And so the question is, how can we learn these latent importance weights? So what we do is we define an adversarial game between D, a discriminator, and W, the latent importance weight function. And so W will try to fool the discriminator by rewriting the original generative distribution and by lowering the amount of low quality samples produced by the generator G. Remark that here the generator G is frozen and it is not further trained in the adversarial process. So we can derive now two sampling algorithms to sample from our latent importance weights. So the first is rejection sampling, where we sample proportionally to the importance weights, and we accept or reject some samples. The second is latent gradient descent, where we follow the direction increasing the latent importance scores. Finally, we show that we can improve the precision of a pre-trained generator at a very low cost. And regarding the ratio of precision over time, we outperform competing methods, and we can achieve higher precision than competing methods. Thanks for your attention.